How you say pulsars are cool. I like that. I'm going to kind of set the stage. Is this one on now? Well, I guess I'll use this. So I'm going to set the stage a bit for the next few speakers. And for those people who know me, obviously this title is my own because I'm obsessed with pulsars. I really do think pulsars are very, very cool, seriously. And when I say that, I'm not talking about this, about the surface temperature, because they are not cool that way. They're about 1 million Kelvin. And they're neutron stars, very good compact objects, the most compact objects we know of in the universe that have a surface. Only black holes are more compact. 10 to 12 kilometer radii, 1 to 2 solar masses. We usually think of the canonical neutron star as being 1.4, but we've learned in the last few years that there's a lot of diversity there. So very, very compact objects. That means that they have incredibly large central densities, where the nuclear physics is not even understood in the centers of the stars. It also means that there's incredibly strong gravity. The surface gravity near the neutron stars is 100 billion times that on Earth. So that causes incredibly strong GR effects. In fact, when you look, there's very strong light bending. If you look near the neutron star surface, you see the majority, or a large fraction, of the backside of the neutron star, depending on how compact these objects are, just due to light bending effects. They rotate, some of them, tremendously rapidly. Most normal pulsars rotate about once per second, but the ones that I really enjoy studying, the millisecond pulsars, rotate hundreds of times per second, and the record holder, which is in Terzan 5, is 716 times per second right now. And that's astonishing when you think about how compact and massive these objects are. That's faster than a race car engine rotates. It's faster than a kitchen blender spins. But yet these things are the size of a city and more massive than our sun. And they're rotating that rapidly. So rapidly that if you could amplify the signals, because these are incredibly faint signals, if you could amplify them and listen to them, you can hear them in the middle of the audio band. It's almost 2 octaves above middle C. It sounds really annoying, kind of like, but I don't have the actual sound, but that's close enough. But it's an actual audible tone that you can actually hear, which is, to me, amazing. When you combine that rotation with the strong magnetic field, because these are dipole magnetic fields, basically, which range from 10 to the 8 to 10 to the 15 Gauss for the magnetars, and Nanda, who's going to be talking next, will talk to you about magnetars. But those magnetic field strengths are billions to trillions or more times the Earth's magnetic field, and way stronger, millions of times stronger than even the strongest magnetic fields we've been able to create here on Earth. So when you combine that rotation with the magnetic field, you have a moving magnetic field that induces an electric field that accelerates charged particles. Those charged particles radiate, but the details of how that emission works, even after 40 some odd years, we are not sure. We basically have a slightly better than hand-waving understanding of pulsar emission. We know in the radio it's some kind of coherent process, but the most energetic pulsars emit beyond the radio as well, clear up through the optical, into the X-rays, and now we have a bunch of gamma ray pulsars as well. So you have accelerating charged particles, you have radiation. When you combine those charged particles which are leaving the system as well as the radiation, that energy is leaving the system, and that luminosity, that E dot that we call it, for the most energetic pulsars can be 10,000 times the total solar luminosity. But that's not coming from fusion, it's not coming from any kind of chemical reactions, that's coming purely from rotation. These are rotation-powered objects. So these are giant flywheels spinning in a vacuum with incredible magnetic fields that cause incredible physics. And this is one of the reasons why they're very cool. They're very exotic objects, period. Another reason why they're cool, and I'm not going to get into this, but a lot of you know this already, is there's a bunch of great stories on the human science side with pulsars as well, including the incredible discovery story, which probably all of you are familiar with Jocelyn and company, and the 2 Nobel Prizes already that have come from pulsar work. So the rest of the talk, I'm going to concentrate on millisecond pulsars, which are those I like the best. And we make millisecond pulsars, or the universe does, via a process known as recycling. So if you have a supernova, which creates a normal neutron star, creates a young pulsar which slows down over time, and after about 50 to 100 million years it dies as a pulsar. But in that supernova, if there was a companion star that survived the supernova explosion so that you have a binary, eventually on stellar evolutionary timescales, that star expands, turns into a red giant, and fills its Roche lobe, causes an accretion disk. This is a low mass X-ray binary at this stage. And that accretion disk transfers mass and angular momentum onto that neutron star. And also, by a process we don't understand, somehow buries the 10 to the 12 Gauss magnetic field by about a factor of 10 to the 4. So eventually, stellar evolutionary timescales end, the red giant phase finishes, we're left with a white dwarf in a perfectly circular orbit around what is now a radio millisecond pulsar. These things then, with their much weaker magnetic fields, spin incredibly stably, and these will last not tens or hundreds of millions of years, but billions of years. But a lot of these we think will actually last Hubble times, once you create a millisecond pulsar. And this stability, that they can last as millisecond pulsars, is why we treat them as clocks. And to me, this is the real reason why pulsars are cool, the fact that we can use them as precision clocks to do basic physics. So here's an example. This is one of the best timing millisecond pulsars known right now. Unfortunately, it's only visible from the Parkes radio telescope. We in the north can't see this guy. But it's an excellent pulsar, and it basically exactly right now, that's the time, I think basically right now, that pulsar has a spin period of that number, and being good scientists, we've got to have an error bar. There's our error bar. And the thing is, that's giving off energy because of the various types of radiation and the particles that are coming off of it. That means it's spinning down. So that last digit is changing about 1 by 1 every half hour. So you can think of that as an odometer on a car clicking off that last digit once every half hour. Now what does that imply? That implies that that digit is changing once every 500 years, and therefore the first 6 digits are changing only about once every millennium. They're stable for a millennium, those first 6 digits. These are incredibly stable, precise clocks, and that stability lets us use them as unique tools to do basic physics. So we do that by the process known as pulsar timing, and I'll give you just 2 quick slides to explain how pulsar timing works. The key point to remember about pulsar timing, if you're not aware how it works, is that we unambiguously account for every single rotation of the pulsar over time scales of years, and that unambiguous is the key point. And when you do it this way, it becomes a phase measurement, not a frequency or a period measurement, a phase measurement, which are always much more precise. So if we have, say, on an observation, here we can make the beginning of our observation, mark it with a very precise clock, say GPS. We can fold our data synchronously with the pulsar's period so that we increase the signal to noise of a pulse. We stack the pulses one on top of each other. We can then measure the average offset of that pulse from the beginning of our observation, and we call that a TOA, or a time of arrival. For millisecond pulsars, we can do that to about a precision of better than a microsecond for a large fraction of the millisecond pulsars. That corresponds to a phase measurement of about a part in 10 to the 4. So, if we want to convert that phase measurement into a frequency measurement, we can see how we get the precise frequencies, because frequency, which is just the spin rate of the pulsar, is just the change in phase over the change in time, d phi dt. So the change in phi, or the phase, is 10 to the minus 4, and 3 years is 10 to the 8 seconds. That gives us 10 to the minus 12, and since these have hundreds of hertz spin periods, that's 14 significant figures just to measure frequency if we count pulses correctly. That's where the incredible precision comes from, in a nutshell. And so we get this, if we want to actually set up a timing solution, we'll go to an observatory, we make a set of observations in 1 day, so this is 1 day's worth of observations. We fold the data synchronously, we stack pulses. When we stack pulses in time, that gives us the frequency we can predict forward. As we predict forward to, those are the measurements, we can make a model to predict forward, and then on the second day we go back to the telescope, we check to make sure our model's right, we tweak it a little bit to make sure that things line up just perfectly, then we can start extending our baseline in time further and further into the future. So we come back maybe weeks later, we check it again. If it's a little bit off, like it is in this case, we slightly tweak our timing solution a little bit. We bootstrap ourselves into this ultra-high precision regime as we time over a longer and longer baseline. So every day we're at the telescope, so here's residuals now, which is the measurements minus the model, which gives us the timing residuals, and you'll see pulsar astronomers make lots of plots like this. So here's 2 years, every day that we're at the observatory, here's a bunch of measurements, and so you'll see lots of little error bars on a certain day, and then we don't come back for another few weeks, let's say. And if you were to take and make a histogram of these error bars and these measurements for this is another excellent timing pulsar that was also found in the south with the Parkes telescope. You get a beautiful histogram with an RMS level of 200 nanoseconds. That means that on average we can predict the arrival time of any pulse that arrives over 2+ years to within 200 nanoseconds. So if we actually publish our results, you get these crazy tables in our publications that look kind of like this, where we have, you know, up to dozens or tens or many, many decimal points of precision. For isolated pulsars, it only takes 4 terms to make a timing solution. The 2 position terms, rate ascension and declination, the spin period, and the spin down rate. If we time for an extended amount of time, we add the other astrometric terms, such as proper motion and parallax, if we're lucky. If it's a binary pulsar, we add 5 terms that take out the travel time delays for the Keplerian elliptical orbit. And if we're really lucky, we have a relativistic binary where there's 5 or more, depending on how you do things, 5 post-Keplerian terms. And Michael Kramer's talk is going to talk to you about those. So here's a great example of that same pulsar I showed you earlier. Here's all the digits of precision in its pulse period, incredible numbers of decimal points in its orbit. Let me just pick out one. I mentioned millisecond pulsars have circular orbits. Here's the eccentricity. It's 2 times 10 to the minus 5 is the eccentricity, but it's hard to understand what that is. That sounds pretty circular. It's really, really freaking circular. This orbit is about 1.5 times the solar radius is the size of the orbit, but the difference between the semi-major and semi-minor axis is 18 centimeters. And the precision of that is known to about 1/10 of a millimeter. And we can do that when you ask the right questions for pulsar timing. And for this pulsar and several others, we can get better than 100 nanosecond RMS timing residuals over many years. All right, so in the last few years, there really has been a millisecond pulsar renaissance, and that's because of instrumentation. Millisecond pulsars, we need incredibly large data rates, lots of frequency channels. Our data rates are many terabytes per day, typically, and so we need Moore's law to allow us to build the proper digital instruments to use our receivers and our pulsar telescopes efficiently. And in the past, we weren't able to do that. So even though most of these telescopes have been around, 3 of these big 4 that I'm showing here have been around for almost 50 years, we've been underutilizing them for almost the whole time for pulsar observations, until just these last few years when our instrumentation has asymptotically approached near to perfection for pulsars. So that's where we are right now, and this is why millisecond pulsars have done great things recently. That's because of instrumentation. Millisecond pulsars, we need incredibly large data rates, lots of frequency channels. Our data rates are many terabytes per day, typically. And so we need Moore's law to allow us to build the proper digital instruments to use our receivers and our pulsar telescopes efficiently. And in the past, we weren't able to do that. So even though most of these telescopes have been around, 3 of these big 4 that I'm showing here have been around for almost 50 years, we've been underutilizing them for almost the whole time for pulsar observations, until just these last few years when our instrumentation has asymptotically approached near to perfection for pulsars. So that's where we are right now, and this is why millisecond pulsars have done great things recently, and are continuing to do so into the future. Here's a good example of that when you look at timing precision over the last 35 years. If you look at the literature and print how well we're able to time pulsars, the trend goes exactly as Moore's law. And that star on the right-hand side shows where we are today. We have of order between half dozen to 10 pulsars that we're timing at the 50 to 100 nanosecond level over extended periods of time. And that's purely caused by Moore's law and digital signal processing. And here's an excellent case in point, something that's a pulsar that's close to my heart. This pulsar was discovered in a survey back in 2004. And at the time, because our instrumentation wasn't so great, it looked like a pretty vanilla millisecond pulsar. Circular orbit, 3 millisecond spin period. It had a slightly more massive companion than we're used to seeing, but basically it looked like a normal millisecond pulsar. But our instrumentation didn't give us great timing. So these times of arrival, which are as a function of orbital phase here, I was using this pulsar as a test system before a lot of globular cluster observations, and the arrival time measurements were only about 10 microseconds. Well, 2 years ago at the GBT, we built a new, absolutely state-of-the-art pulsar instrument called Guppy, and we predicted that we'd be able to improve our timing precision by a factor of between 3 and 5 on this pulsar. And this we decided to use as our first test source for the new instrument, basically, because of these data points right here. These data points at orbital phase 0.25, which is conjunction, where the pulsar is behind the white dwarf, appear to be slightly delayed from the rest of those arrival times on 3 different days. So it seemed to be systematically delayed. One thing that can explain that is Shapiro delay, which is a little diagram here. If the pulsar is behind the white dwarf, those pulses go into and out of the gravitational potential, and that causes a slight delay in their arrival time, so we see them delayed. Well, we made observations over an intense 1-week observing session. The red points are our data points. There's about 1,500 arrival times. We get this incredible cusp. That's the exact prediction of what you get from a strong Shapiro delay signal. It was very surprising to us, especially how peaky, how sharp that cusp was, because that sharp cusp implies that the orbit is nearly edge-on. And in fact, the Shapiro delay, when you measure the exact shape of that, you get 2 parameters. You get the mass of the companion, which is half a solar mass to very high precision, and an inclination, which is within 1 degree of being perfectly edge-on, so we got lucky. When you combine those 2 measurements with the mass function, the Keplerian mass function, you get the mass of the pulsar, and that turned out to be basically 2 solar masses. Thank you. And when you simply take those 2 relativistic parameters on top of the Keplerian solution, it completely flattens the residuals and makes this thing a perfect timing pulsar. This is what the data, the raw data, look like around the peak, and you can see it follows that Shapiro delay prediction of general relativity perfectly. So what does this mean? Well, this just happened to be this one measurement of 2 solar masses turned out to be very exciting for nuclear physics because it strongly constrains the equation of state of dense nuclear matter. And so this diagram shows the equations of state, which in this representation show how mass and radius are related for the neutron star. And the red line is the mass of this pulsar. The curved lines are possible equations of state, and there's so many of them because we don't understand the nuclear physics of dense matter very well. But the neat thing is that any line which curves over and doesn't meet that red line, so these guys down here, they're ruled out because they can't make 2 solar mass neutron stars. It's basically that simple. So many soft, so-called soft equations of state, which bend over so that they can't get to high masses, are ruled out by this one measurement. So it shows you the types of things that we can do, basics physics-wise, by making the right pulsar measurements. All right. So one of the main things that we're going for in these millisecond pulsars nowadays, most of the people who work on pulsars are pushing towards a direct detection of gravitational waves within what we hope is the next 5 or 10 years. And to do this, we're making what are called pulsar timing arrays, where we need excellent millisecond pulsars spread across the sky. And we're looking for nanohertz frequency gravitational waves that are going through the galaxy. We need lots of pulsars, which is currently our biggest limitation, because we don't have enough good pulsars, because the significance of any detection scales basically linearly with the number of millisecond pulsars that are being timed. So the experiment is effectively something like a 10-ish year experiment with 20 to 40 millisecond pulsars at the 100 nanosecond level. And there's 3 big groups internationally that are working on this now: Nanograv in North America, the Parkes Pulsar Timing Array from Australia, and the European Pulsar Timing Array using the 100-meter class telescopes in Europe. And together we're starting to work and share our data to become the International Pulsar Timing Array as well. So these gravitational waves that we expect to detect are coming from supermassive black hole binaries spread throughout the universe. And by supermassive, I'm talking 10 to the 9 to 10 to the 10 mass systems. We don't expect to see the mergers. We're expecting to see the orbits when there are thousands to tens of thousands of years before merger. Because at that time, those orbits are in years. They're year-long timescales. And so we will see delays in our pulses with year periods in our data. And those delays can actually be tens of nanoseconds. This 2-point correlation function here, known as the Hellings and Downs curve, and that's kind of the signal that we're looking for. surveys undergoing. All of those, basically, those big telescopes that I showed you, as well as Effelsberg. And in the last 3 years, we've more than doubled the number of millisecond pulsars. This is also completely due to Moore's law. Our data now are much better than they were 5 or 10 years ago. The other thing that's really helped out is Fermi. A big chunk of those recent millisecond pulsars have come because Fermi, the gamma ray satellite, has showed us where to point on the sky. So Fermi has an unassociated source that we don't know what the source is. We point our radio telescopes and find a millisecond pulsar. And the neat thing is these are different. These are a different batch than we're going to find with the all-sky surveys. They turn out to have quite different properties. And we've found 43 of them and counting this way. And this shows what happens with pulsar timing. So if you find these in the radio, you time them over a time period of a year or two to get a timing solution. Then you know exactly how the pulsar rotates. You're going to take then the 3,000 photons over 3 years from Fermi. That's only 3 photons per day. You know exactly what pulse phase to assign each photon to, and everything lines up beautifully, and you get this very, very sharp gamma ray pulse profile, even though this is over 24 billion rotations of the pulsar and 560 binary orbits. I think that's pretty astonishing. So the other thing we get for free from these surveys, besides good new pulsars for pulsar timing arrays, are exotic systems. These are always fun for pulsars. Here's a good example. Here's a missing link system that was found in the optical, and people thought it was a cataclysmic variable or a low mass X-ray binary about 10 or 12 years ago. It actually had an accretion disk. Apparently that accretion disk went away. This thing turned on as a millisecond pulsar. It's probably going back and forth between those states. But this is basically a missing link system. Very interesting system. Another one that was just announced last year, the so-called Diamond Planet. This is basically a Jupiter-mass planet around a millisecond pulsar in a compact binary. And because of the compact nature, the density of that must be at least 23 grams per centimeter cubed. So it's basically the core of a carbon-oxygen white dwarf, likely diamond-like. So quite interesting, got a bunch of press when it came out. And just at this meeting, 2 other systems very much like it have been announced. And we can find these things because we have extraordinary timing precision of about a millimeter per second in velocity. Compare that to the meter per second precision from optical radio velocity surveys. The last thing I want to mention, the last exotic, there's some neat things that have happened with triples. A binary was found in a highly eccentric orbit with Arecibo a few years ago. It had a main sequence companion. That doesn't jive with the standard recycling scenario, which gives you a white dwarf in a circular orbit. So the idea was that this system likely had a triple origin where the white dwarf was kicked out. So people did some theory, and they said that because of triple dynamics, there should be a small number of these systems that have survived and did not kick out one of the stars, and so we should see millisecond pulsars and triple systems in the galaxy. Well, sure enough, just this year with the Green Bank telescope, we found the first such stellar triple system with a 1.6-day inner binary and a 327-day outer binary, both of which are stars, and so not planets, but stars. And that inner orbit's already showing secular perturbations. It's going to be a beautiful test bed for non-Keplerian dynamics. So in the future, there's lots of surveys going on. There's about 10,000 pulsars to be discovered, at least in the galaxy. We're currently sensitivity limited with our telescopes, but because of that instrumentation, we're still going to find a lot of these things. And maybe some new holy grail systems as well, such as a sub-millisecond pulsar, pulsars around black holes, including Sagittarius A star, and maybe even a millisecond pulsar binary in a glider cluster. And these new telescopes that are coming online over the next 5 to 10 years, especially Meerkat, FAST here in China, and LOFAR are going to be fantastic for pulsar research, and will all eventually lead the way to the SKA, which is going to do great things for us. The last thing I want to mention is that on the not-so-happy front, the Green Bank telescope, which I've showed you a lot of the science has come from, was just announced last week from a portfolio review of the National Science Foundation. They suggested that we divest of that instrument, which basically means stop paying for it. And if we lost this telescope, it would be a disaster for pulsar research, not to say anything of my own personal career. So as a final note, despite this one little blemish of not so great news, I think pulsar science is in a great time right now. And so my summary is, pulsars are cool, seriously. Thanks.
Well, thanks, Scott. That was a great talk. So we have time for a few questions. Okay, third row.
can I ask what sets the high frequency limit for your pulsar timing accuracies and your gravitational wave detection plus?
So the high frequency limit is set by the way we integrate up the gravitational wave strain between us and the pulsar. It's based on the timing baseline. The longer we integrate in time, we go deeper and deeper. So for short wavelengths, we can't integrate very long in time, and it's less sensitive. That's the high frequency limit.
When you detect the gravitational waves for millisecond pulsars, can you tell from which direction the gravitational waves coming?
Potentially. So there are some ways, for instance, if there's a supermassive black hole binary relatively nearby in the universe, if we have enough sensitivity in our pulsar timing array with good enough pulsars, there are ways to actually get a rough direction. And then there's even possibilities if you can get electromagnetic detection of where that black hole is, you can actually potentially phase up the array and determine the distance to all your pulsars to, light year, sub-light year accuracy, and then get a very precise position. This is probably not going to happen anytime in the near future, though. It's a long way off. But it's possible.
That was a wonderful talk, Scott. On the gravity wave backgrounds, there's always been also the cosmological speculation that maybe some exotic cosmological models could be constrained by the fact that they provide a gravity wave background. Now, the merging black holes in some sense are the mundane version, because if they are not there, we would be really worried at some level. Do you think there is potentially a way in which, in some statistical sense, you could tell the difference between the two kinds of background?
Yes. So the other types of backgrounds that I was talking about, for instance, cosmic strings, it causes a potential background, as well as relative gravitational waves from inflation. The neat thing is those have different spectra, and we are sensitive to the spectral index of the gravitational waves for the stochastic backgrounds. So if we make a detection of gravitational waves, we should be able to tell if it has a spectral index of -2/3, say, which is what we expect from black holes, as opposed to from the inflation or from cosmic strings, which have different spectral indices.
Okay, last question.
Okay, when you talk about this two solar mass neutron star, you say this can rule out a lot of soft state. Yeah? So the underlying assumption is all the neutron stars should have the same state. Yeah? So is that possible that different neutron stars could have, different state?
It's probably possible in some way, but I think most people who work on the dense equation of state of nuclear matter think that you basically lock into a ground state of nuclear matter when you create a compact star like a neutron star. And because of that, there's basically one family of solutions where only the effective free parameter is the mass. I'm sure theorists can come up with ways to split that off, but I think most people think that that's the ground state of nuclear matter and that there's only going to be one relation.
Okay, so let's thank Scott again.